Greetings and welcome to the Chemistry 151 lecture for Chapter 3, Part 1. We'll look very intensely at chemical nomenclature, which is the naming of chemicals. And as a chemist, you must know which chemical you're dealing with. We'll see the reactivity difference can be quite different upon just adding an additional atom or taking one away for that matter. So this one will look at the rules and how you can figure out how to name something, and also what the formula is once you have the name. But first, let's have a relevant joke. Anyway, so bear with me. Two chemists walk into the bar, and the first chemist says, "I'll have some H2O." And if you don't know already, or maybe you do, H2O is the symbol for water. So the bartender gives them a clear liquid, and it's in a glass, and drink it down. Good old cold water sounds awesome. No problem. Second chemist looks at that and goes, "Boy, that looks pretty good. I'll have some H2O too." Now, there's a play on words here, of course, TOO versus TWO. But anyway, a clear liquid in a glass arrives from the bartender. They drink it down and die. And I apologize for the morbidity of this, but it does go to show the difference between one extra atom. So water, H2O, that's good to drink. We all need that every day and stuff like that. We use it for so many things. H2O2, which is just one additional oxygen atom, is a whole different story. It looks just like water, all right? If you ever looked at hydrogen peroxide, which you can buy in the store and stuff like that, it looks just like water, but you wouldn't dare drink it, all right? It's an oxidizing agent. It does all kinds of, it would rip your throat out and stuff, horrible things. So the silliness of this joke aside, it does show the importance of what we're talking about, because H2O and H2O2 are very similar. One has 4 atoms, one has 3. One additional oxygen atom makes a big difference. You wouldn't want to drink hydrogen peroxide, but you certainly do want to drink water every day. Nomenclature is just a set of rules that chemists have decided upon, and it's a way to describe compounds, all right? So it's a way to quickly say which compound you want. And like I just showed you, an additional atom or one less atom can make a big difference in the reactivity. So you have to be very careful. Arguably, this is the most important chapter of Chemistry 151, because if you don't know how to ask for the right chemicals or tell others which chemicals you have, might be kind of a bad thing. Compounds are a combination of 2 or more elements in definite ratios by mass. And we talked about this earlier. The only pure substances really are elements or compounds. Compounds are when you take elements and put them together to make a bigger kind of piece. The definite ratio by mass is important. Water, H2O, is always H2O. It's never, for example, H2O2, which would be hydrogen peroxide. It's never just HO or HO2 or anything like that. So the definite ratios make them very predictable. When you make a compound, the character of the elements that they came from becomes quite different. And as an example, water is made from hydrogen and oxygen. Hydrogen is a flammable gas. Oxygen, flammable too, does some different things. But water is a liquid, and water is good for you and you need so much every day, etc., etc. Now, as you break a compound down, you finally do get down to the smallest piece of the compound called a molecule. And a molecule, if you break that up, it will no longer have properties of the compound. Remember that the smallest piece of an element is an atom. So if you broke a molecule up, you'd probably be breaking that up into the atoms, and you'd have different properties from there. What the? Bond? Chemical bond? Okay, you're seeing my enthusiasm, shall we say, for a type of movie genre. It's not James Bond, of course. This is the chemical bond. And anyway, this is so embarrassing. But anyway, instead of 007, which is James Bond's thing, let's call this 008. And I'm changing it to 8 because in bonding, number 8 is an important number. And it's going to take a little bit for us to get to why number 8 is important, but bear with me. There is something kind of exciting about that. So chemical bonds are super important, and there's really 2 types of chemical bonds, and those are called ionic and covalent. Ionic bonds are stronger, but covalent bonds are more flexible, and for life, both of those are really important. Normally, if you have a normal atom, the number of protons, which are positive, and the number of electrons are equal. So if the protons and the electrons are equal to each other, you have a neutral atom. It doesn't have leftover positive or leftover negative charges, and that's cool. However, in the real world, it's quite easy to gain or lose an electron. And if you gain or lose an electron, now you don't have equal numbers of protons and electrons. So for example, if you had extra electrons, you'd end up with a negative charge. If you had extra protons, you'd end up with a positive charge. So a positively charged or negatively charged atom is called an ion. And we'll use this term quite a bit as we go through it. So an ion is just an atom with an unequal number of protons and electrons. If you lose an electron, then you have more protons than you have electrons, and the new ion has a positive charge. And a positively charged ion is called a cation. On the other hand, you can gain one or more extra electrons. So now you have extra electrons relative to protons. That gives your atom, an ion, a negative charge. And a negatively charged ion is called an anion. So a cation is a positive ion, and an anion is a negative anion. Cation and anion may be somewhat new to you. It's not too hard to remember because cats have pos. Cat ions are positive. All right, I know it's kind of silly. I do like cats, I admit. But anyway, cat ions have more protons than electrons, and anions have more electrons than protons. But if you remember that cats have pos, or cat ions are positive, you're going to be good to go. The symbol for a cation is written by adding a positive charge as a superscript up in the right-hand corner of the element. So as an example of that, sodium likes to lose, we're going to see, one electron. And in the process of losing one electron, you can see in the lower right corner, it still has 11 protons. Remember, if you change the number of protons, you change the nature of the atom itself. However, with only 10 electrons, now you have 11 positive 1 protons and 10 negative 1 electrons. Sodium likes to, as an ion, likes to be positive 1. All right? It likes to have, we're going to see just one less electron. A little bit of stability right there. So sodium likes to form a +1 cation. And if you can't wait for my 008 significance of 8, notice there that there's an 8 right there. That has something to do with the 008, but we'll talk about it later. So if you have a positive ion, a cation, it's going to have lost electron or electrons. In this case, you have 11 positive 1 protons on sodium and only 10 negative 1 electrons. So 10 times negative 1 plus 11 times positive 1, that's the origin of that positive 1 charge. You can do the same kind of thing, though, for anions, because electrons like to go somewhere. And the negative charge is also a superscript in the upper right-hand corner. So here's maybe where the electron would go. Maybe the electron decides to wander over to chlorine. And notice that on the left, chlorine, which is number 17 on the periodic table, chlorine has 17 protons, and a neutral atom of chlorine would also have 17 electrons. However, we're going to see that chlorine likes to gain 1 electron, and when it does, now it has 18 electrons, more electrons than there are protons. So that extra negative 1 electron is going to give that a negative charge. Notice that we're calling this anion a chloride. In chemistry, the convention is to give the negative charge species an IDE ending. So chlorine becomes chloride when it gains electrons. And again, you're probably seeing here lots of 8s. That'll be a future lecture. We'll talk about what's going on. Opposite electrical charges attract. So when you have a positive sodium and a negative chloride ion, there's going to be a pretty strong attraction right there. And that thing is called an ionic bond. So an ionic compound is just a compound where the glue, if you will, that holds the atoms together, it comes from the attraction between positives and negatives. So in this case, sodium chloride is that. Now, we usually will write sodium chloride, if you will, as 1-to-1 like that. But in reality, you've got this elaborate three-dimensional network where there's alternating positive, negative, positive, negative, positive, negative in all three directions. Very, very strong, really intense glue, if you will, that holds the atoms together. But usually we'll just refer to them as NaCl. Here's a video that actually shows the formation of NaCl.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
The next time you or you put table salt on French fries or something like that, remember this video. There's a lot of energy released when sodium, the element, and chlorine, the element, come together to make sodium chloride. Sodium got molten metal. They melted it to make it a little bit more reactive. And the chlorine is kind of a green gas. And when they come together, a lot of energy is released. Wow. Ionic compounds usually form very crystalline solids, which means you can actually see like little kind of corners on them. If you look carefully at table salt, you'll see it. You'll also see it on other types of solids too. The ions do vary in size and charge, but generally speaking, because those ions go on in three dimensions, you're generally going to have very high melting and boiling points. So it's difficult to melt things and boil things. Here's an example. Sodium chloride has a melting point of 800 degrees. So if you want your sable salt to form a liquid, not with water, mind you, that would be a solution. If you want the actual sodium chloride to become a liquid, you have to heat it up to 800 degrees Celsius, 804, and that's pretty hardcore. It shows the strength of these ionic bonds. However, magnesium oxide, which is a Mg+2 and O2- compound, is even higher. That +2, -2, it's kind of like a double handshake, and it's harder to break up than sodium plus chloride minus's single handshake, so it takes an even higher amount of energy to make that melt. Groups 1A and 2A have just metals. Group 1A was the alkali metals, and Group 2A were the alkaline earths. And when those metals in those groups react to make ionic compounds, they have a predictable charge. And Group 1A will always be +1, and Group 2A will always have a +2. And they do that because, as we're going to see later, they're going to end up looking somewhat like a noble gas configuration. And we'll talk more about what that means later. But anyway, for right now, groups 1A love being +1, and groups 2A love being +2. Now, on the other side of the periodic table, group 6A and 7A, which are nonmetals, group 6A has oxygen, sulfur, etc. Group 7A has chlorine, fluorine, bromine. The 7A is the halogens. They can attain this noble gas configuration by gaining electrons. So oxygen likes to gain 2 electrons and sulfur. Chlorine likes to gain 1 electron. So you can hopefully see that some of the groups have predictable ionic charges. So groups 1A and 2A will always be positive. Groups 1A will be +1. Group 2A will be +2. On the other hand, groups 6A and 7A always going to be negative. 6A wants to gain 2 electrons, like that we can see in the pictures right there. Group 7A wants to gain just 1 electron, and so those will always be -1. The octet rule is something we'll talk about more later, but if you can get this magic 8, you're going to end up with a noble gas configuration, all right? Isoelectronic is a term we'll use once in a blue moon. It means the same number of electrons. So if you have a noble gas configuration for one of these ions, it will be isoelectronic with noble gases. Another way to think about this is noble gases are kind of the cool kids on the back of the bus, and if you are in the bus, you probably want to be like the cool kids. So if you gain or lose electrons to look like them, you'll be one of the cool kids too. Now, we're going to talk a lot more about this in a future chapter, but for right now, all the noble gases do have 8 electrons in their valence shell, the outer shell, except for helium. And again, we'll talk about this in more detail later. So when sodium chloride forms, all right, the sodium has a electron configuration which is like neon. Chloride has an electron configuration which looks like argon, and they come together to form sodium chloride. And that's where the origin of this 8 thing is. And again, we're going to talk about this more later. Here's 2 and 6 on the sodium ion for 8. Here's chlorides 2 and 6 right there. So you can see there's something about this number 8 here we're going to see that's important for bonding. This is some of the periodic table with some of the more common charges for things, all right? And it's kind of hard to see, but groups 1A always like being +1. And group 2A always likes being +2. And if you go to the other side, group 7A likes to be -1, and group 6A likes to be -2. Now, a lot of the group 3s like being +3. We're going to see it's not all of them, but there's a lot of them. And another thing to see is that the non-metals, which are those light blue ones in the upper corner, they're always going to be negatively charged. And if you look at the metals, which is all the yellow atoms, and hydrogen for this matter too, they're going to like being positive, all right? And we'll talk more about the rules here coming up. Aluminum, if you're curious, then is a group 3, so it most likely makes a +3 charge. Nitrogen, if you're curious about it, nitrogen's charge is going to be the group number -8. So nitrogen is in group 5A. It would be number 7 right there. All right, so 5, the group number, -8 is -3. And you bet that 8, again, comes from that noble gas configuration. And again, we're going to talk about this more later too. If you think about all the metals, some of them have predictable charges and some of them we don't know. So let's focus right now on what's called the fixed charge metals. And those are just metals with a predictable positive charge. Now we've already seen that group 1A metals like potassium and sodium and lithium and cesium, etc., they like to be +1. Give them that noble gas thing. Groups 2A, which are magnesium, calcium, strontium, barium, etc., they like to be +2. And there is also this thing down here called the stairs. Look on the periodic table, start at aluminum, and you can see that aluminum, gallium, and indium, that's a 3-step kind of thing. All of those are +3. And then you go down 1 to zinc. Zinc and cadmium are 2. Those are both +2. And silver down there is always +1. Now, why the fixed charge metals are important is they'll be really nice to know in bonding. And the stairs, those 6 right there, plus groups 1A and 2A, we know their charges all the time, which is really cool. The main group anions, the negative charges, also are predictable. And basically the main group anions, most of them are 5A, 6A, and 7A. And like you saw, you take the group number and subtract 8 in order to figure out what their charge is going to be. Notice the names too. We're changing all of these names to ide. And ide tells the chemist that it's a negatively charged ion. So chlorine in group 7, 7 minus 8, That's where the -1 on chloride comes from. And again, we'll change it from chlorine to chloride. Oxygen in group 6 minus 8 becomes -2. That's the oxide ion. Phosphorus in group 5 minus 8, -3 on phosphide. And if you wanted to do it for carbide, which does happen once in a while, carbon is group 4. In this case, 4 minus 8, -4. That's what the carbide ion is. Some species we don't know for sure what their charge is, and these are called variable charge cations. So while we always know that groups 1A, groups 2A, and the stairs have a fixed charge, a lot of the metals we don't know, and that includes the transition metals, the B block elements kind of in the middle, as well as lanthanides and actinides at the very bottom, and there's also a few metals under the nonmetals. All of those are considered variable charge. Well, we don't always know what the charge is going to be. So for chemists to talk to each other about which one they're dealing with, we're going to use Roman numbers to express the charge. Here's two examples of chromium. Chromium +2 and chromium +3, which are both very common. We would call chromium +2 the chromium 2 ion with a Roman numeral, and chromium +3, we would call it chromium 3 ion. So that's how people distinguish one from the other. If you told me you had a chromium ion, I would not know which one it was, all right? And, I have a PhD, I should know everything, right? Well, no, I don't. And no one should. So the Roman numerals are really important. You've got to include them if it's one of those transition metals, lanthanides, actinides, stuff like that. And conversely, if you see, for example, on the bottom, iron Roman numeral 3, that would mean iron +3. And iron Roman numeral 2 would be iron +2, etc., etc. A polyatomic ion is another thing that pops in once in a while. Poly means many, so many atomed ion is what a polyatomic is. And a polyatomic ion is just something that's unfortunately very, very common. This is an example of one. It's sulfate. You can see it's a sulfur, 4 oxygens, and it has a -2 charge. So it's a many atomed ion, 5 atoms coming together, and overall there's a -2 charge. And sulfate is one example of how these things roll. There's a lot of these out there, and you've got to start becoming familiar with them / memorizing them because they're so important. Some of them are more common than others. So for example, down here, this is sulfate we talked about earlier. Nitrate, NO3-1, is actually very, very common. Cyanide, you've probably heard of, is a horrible poison, but it has other cool uses too. Most of these ions are negative, but there is one which is positive, and that's the ammonium cation. And ammonium is one of the few positive ions that's out there. So start figuring these out and seeing how they work. They're pretty important in chemistry. You should know the name, the formula, and the charge, like what it's like and stuff. All those things come in really handy. Now, one way to help you learn polyatomic ions is to talk about Nick the Camel. And no, I don't think I've totally lost it yet, but Nick the Camel is an expression that's used sometimes to help learn polyatomic ions. And if you look at the top right there, Nick the Camel Brat ate icky clam for supper in Phoenix. And you're probably like, okay. But notice there that I've underlined some of those pieces there. And the underlined part represents one of the polyatomic ions. So for example, Nick, the first one there, Nick is a reference to nitrate. In Nick, you can see the red letters. There are 3 consonants. And just as a quick reminder, vowels are A, E, I, O, U, and consonants are basically everything everything else. So there's 3 red letters, 3 consonants. That means 3 oxygens. And because there's 1 vowel, all right, that means there's a -1 charge. So from Nick, you can kind of deduce that nitrate is NO3 minus. And you can see all these other ones in here too. So for example, bromate is Br, all right. The Br is bromine. There's 3 consonants, Br and T, so that's 3 oxygens and 1 vowel, all right. Here's our friend's sulfate from before. Supper is sulfur, all right. There's 4 consonants, so that means 4 oxygens, and there's 2 vowels, a U and an E, so sulfate is a good way. And if you want, you can say that he also had crepes for dinner, which helps with chromate. It's up to you how far you want to go with this, but anyway, just realize this is one way that people have had good success in learning these things in the past. To name compounds, you put the name of the cation with a space and then the name of the anion, and the name must reflect the formula, and or there's going to be special rules for these kind of things. Now, some of these make sense, and remember the anion gets the ID ending. So NaBr would be sodium bromide, and that formula makes sense now because sodium is a +1 cation and bromide is a -1 anion. The next one is magnesium sulfate. Magnesium is a +2 metal, and sulfate is a -2 polyatomic ion. So they come together 1 to 1 like that, magnesium sulfate. Now, the next one is an example of a variable charge metal, which is tin. Tin can exist as both +2 and +4. Chloride is always -1. So we saw that back with sodium chloride, and it still applies here. Notice how there are 2 chlorides balancing the tin. In the first example, that means that tin is a +2 charge. You always want to have a neutral compound when this is done. So we would call this tin 2 chloride. And the next one would, of course, be tin 4 chloride. You've got 4 -1 chlorides balancing the tin. This would be a +4 tin. And then the last one, aluminum oxide is the name. Aluminum is always +3. It's one of the stairs. Oxygen is -2 always. When they come together, you have to find a common denominator. So the 3 on the aluminum +3 and the 2 on the -2 oxygen, multiply 3 and 2 together to get 6. And if you take that common denominator and divide it by the 3 of aluminum, you're going to need 2 aluminum ions. And 6 divided by the -2, if you will, of the oxygen, you're going to need 3 oxide ions to make it balanced. So notice in all of these, we're definitely trying to get a neutral compound, and that's super important in this section. If it's a variable charge metal, we got to put that in. You do need the polyatomic ion name and charges to figure it out. Oh boy. Formula of an ionic compound, the formula will always show the lowest possible ratio of atoms in the compound. So, for example, when you have magnesium and phosphate coming together, magnesium is +2 and phosphate is -3. And like we talked about earlier, a common denominator between 3 and 2 is 6. So if you go 6 divided by the 2 on magnesium, that's where the 3 comes from. And 6 divided by 3 on the phosphate is why you need 2. Notice that we put parentheses around the phosphate because there's more than one. You wouldn't want to write PO42 because it would look like PO42, where you'd have 42 oxygens and 1 phosphorus. That doesn't make any sense. So if there's more than one polyatomic ion, you use parentheses. Don't use parentheses under any other circumstances here, only if there's more than one. Practicing these is really important. It's all stuff that will fall for you, but you do have to work on it, of course. Here's just some examples. The first one that I've done for you, and we'll talk about the other ones. So sodium and chloride coming together makes NaCl. Calcium and oxide coming together, calcium oxide. So notice that +2 and -2, they cancel out. No leftover charges is what we want. We're good to go. The next one is aluminum sulfide. And if you want to use common denominator, that would be the best. So 3 and 2, 6. Notice I'm multiplying 3 by 2 to get 6. That's the common denominator. Anyway, then 6 divided by 3, 2 aluminums, and 6 divided by 2, 3 sulfurs. You can look up what's called the crossover method, which doesn't work all the time, but it's better than nothing. Notice how the 3 on the aluminum went down by the sulfur, and the 2 on the sulfide went down by the aluminum. That doesn't work all the time, but it does work a lot, so just FYI. Calcium and chloride, all right, so chloride has a -1 and calcium's +2. So you're going to need 2 -1s to balance the calcium. And the next example is the opposite. Sodium is +1 and oxygen's -2. So you're going to need 2 +1s to balance the oxygen. The next one, calcium and nitride coming together makes calcium nitride, Ca3N2. Continuing on, lithium and bromide, that's 1:1, so they combine just 1:1 ratio. Magnesium and fluoride, you can see there's a +2 on the magnesium. Fluoride's only -1, so we're going to need 2 of them. That's magnesium fluoride. Aluminum and iodide, same kind of thing. We're going to need 3 -1 iodides to balance the aluminum. The next one is a combination of polyatomic ions. Ammonium is NH4+ and phosphate's -3. But just like with the other ones, you're going to need 3 +1 ammoniums to balance the phosphate. We would write this as parentheses, NH4 parentheses 3 PO4. And again, if you use more than one polyatomic, you should use parentheses. You wouldn't want to write it as 43 hydrogens. That would be very creative, but not the most efficient. And then the last ones, strontium and phosphide, come together as SR3P2. K and Cl come together as KCl. And again, the goal here, make them neutral. All right, use parentheses only when there's more than one polyatomic. Don't use parentheses for anything else. Here's another type of a guide where you can figure out what the formula is going to be for these different combinations and the name as well. I'll help you with the first one there. Sodium and bromide ions would come together to make NaBr, and you'd have sodium bromide. And then aluminum, the next one down, and bromide would be AlBr3, aluminum bromide. The next one, SnBr2, would be the formula for tin-2 bromide. And the last one on that column would be tin-4 bromide. And you can do all of them, and I encourage you to practice this. Practice is the way to make these better. Remember that all the names with the tins are going to have the Roman numerals in them. And the Roman numeral, again, reflects the charge on the metal. It doesn't reflect the number of bromides or anything like that. Here's another example, but this time with some polyatomics. So again, I'll show you how this works. Ammonium, NH4+, and OH-, those come together 1:1. So the formula would be just NH4OH, no parentheses. The name is ammonium hydroxide. Calcium is a +2. So when calcium and hydroxide comes together, you're going to need 2 hydroxides. So you'd write that as Ca parentheses OH parentheses 2. And that would be the way to show that you've got calcium hydroxide. You can practice the other ones and stuff, no problem. Again, notice how the formula changes depending on the charges of the cations and anions. So try to practice this stuff, all right? Find a source online or on our website and just go through and make sure that you know how these things work. Acids are also important, and a lot of times they're thrown in this section. And acids have H plus as the active ingredient. H plus is a source of energy in chemistry, and sometimes adding an acid will allow you to make things happen that wouldn't have happened normally. Acids are so important to chemists that usually the H is listed first. So for example, HCl would be hydrochloric acid, we'll see. HNO3 down there is nitric acid, but again, the formula is listing the H's first. So the middle one, H2SO4, that would be sulfuric acid. Acids are pretty important in chemistry.
When nitric acid, HNO3, encounters a water molecule, it forms an acidic solution by donating a proton, the H plus ion, to the water to form a hydronium ion and a nitrate ion.
The hydronium ion is sometimes listed H3O plus, and sometimes it's listed just H plus. For us, it's the same thing, but think about that as the source of energy. So the acids will break up in water. The H pluses, if you will, fall off, and the rest of it is left over. So for HCl, that would be H plus and Cl minus. In nitric acid there in the video, you can see it's H plus or hydronium, and the nitrate ion.
NaOH, sodium hydroxide, is a strong base because it dissociates completely. In aqueous solution, it breaks into sodium cations and hydroxide anions.
Acids are important in chemistry, but bases are important too. Acids and bases kind of can help each other out sometimes, and we'll talk about this more in the 200 level. A base is just a species that has what's called a hydroxide anion, and hydroxide is one of the polyatomic ions. And if you have the hydroxide by itself, there's a lot of energy possible. A base is a metal hydroxide, so you can see the examples there. This sodium is a metal, potassium is a metal, barium is a metal. So sodium hydroxide would be NaOH, KOH would be potassium hydroxide, and the last one there would be barium hydroxide. And similar to an acid, in water, the hydroxide leaves the metal and it goes off to do its cool things. And again, we'll talk a lot more about this, but acids and bases are both just great sources of energy in chemistry. Acids give off an H plus, or that hydronium, and hydroxides end up giving the OH minus ion, which does a lot of stuff. So here's some examples. Let's just kind of go through them and you can test yourself. And again, I encourage you to do this as much as possible. So NaCl, sodium ion chloride ion. Sodium is a main group metal. It's a fixed charge metal, so we don't need a Roman numeral. This would be just sodium chloride. The next one is similar. It's calcium, and that's a group 2A fixed charge metal, and bromide, which is a non-metal. All right, bromide's -1, calcium's +2, etc. So they charge out. But anyway, the name would be just calcium bromide. Now, Mn may be an atom you're not as familiar with, but it's manganese. And it might be tempting, following the previous examples, to call it manganese fluoride. But if you looked at the periodic table, manganese is a transition metal. And that means it's going to have a variable charge. And anytime you have a variable charge metal, you need a Roman numeral. We didn't need a Roman numeral on sodium and calcium because they were part of groups 1A, groups 2A, or the stairs. But manganese is not part of that, so we're going to need a Roman numeral. Now, if you just look at that at first, it might be a little confusing, but the non-metal is the key to figuring it out. So just like chloride, fluoride is a -1 ion. It's group 7, 7 minus 8, -1. And fluoride is always -1. There are two -1 fluorides balancing that manganese. And remember, everything has to be equal. So manganese here is going to be a +2 charge. It's going to balance the two -1 fluorides to give the overall 0. We're going to put a Roman numeral next to the manganese. This thing is manganese, Roman numeral 2 fluoride. And I would call it manganese 2 fluoride. The next one has a polyatomic ion. If you're learning polyatomics, recognize them by the fact that they'll have 3 or more types of atoms. So let's look at the previous examples. Sodium and chloride, 2 types of atoms. All right, so that's no polyatomics. The next one, calcium and bromine, 2 types of atoms, no polyatomics. The third one, manganese and fluorine, 2 types, no polyatomics. But here, gallium, and with this one, we definitely have a polyatomic. That's the sulfate ion we saw earlier. So that's compound is a gallium sulfate. Gallium is part of the stairs, so we don't need a Roman numeral. We'll just call that one gallium sulfate. The next one also has a polyatomic ion, NO3, you can see is in parentheses right there. That's the nitrate ion. It's -1. There's 3 of them because aluminum is one of the stairs. It's always +3. So that one you would call just aluminum nitrate. The next one now we're going to go in the opposite direction. So hydrochloric acid, hydro is a hydrogen +1. Chlorine we've seen is almost always negative. So that would be just HCl. That would be the name of it, or the formula for it, excuse me. The next one's a little bit tricky. Iron 3 oxide. Remember the iron Roman numeral 3 means Fe3+. And we've seen earlier oxygen as oxide, group 6 - 8, oxide O-2. So when we put these together, we want to have a neutral compound. 3 times 2 is 6. So if you don't know, then 6 divided by 3 means 2 irons. 6 divided by 2 means 3 oxygens. Fe2O3. Score. Potassium hydroxide. Potassium is K, it's +1. OH- is hydroxide, one of the polyatomic ions we saw earlier. They come together 1 to 1. That's going to be just KOH. And then finally, the last one, chromium 3, means chromium +3. Iodine group 7, 7 - 8. Iodine -1. So when they come together, you're going to have 3 -1s for every chromium. Chromium 3 iodide would be Cri3. And again, my call once again, practice, practice, practice. There's lots of sample things on our website and also online. You can use, the more you practice, the better you'll get. Covalent bonds are when you share electrons, and covalent bonds are mostly just between non-metals. A molecule is a group of atoms held together with covalent bonds, and that's kind of a cool thing. So nonmetals and nonmetals, when they come together, they're going to make bonds too, but they're going to be covalent bonds, shared electrons, all right? And they get their noble gas configuration with that magic and weird number 8 by sharing electrons. So instead of having true positives and negatives, like in the ionics, you can actually have electrons being shared. Water is an example of a covalently bonded molecule. And in water, you have nonmetals reacting with nonmetals. Remember that hydrogen is a nonmetal. It's the one over there by itself. And oxygen, definitely a nonmetal. So when they come together to make water, water has hydrogen and oxygen, all nonmetals. We would call this a covalent bond, shared electrons. And that's kind of a cool thing. Let's figure out which of these molecules listed are bonded through ionic or covalent bonding. And remember that ionic, you have to have something positive and something negative, usually a metal and a nonmetal. The covalent bonds will all have nonmetals. So you can see in the first one, phosphorus and chlorine. All right, phosphorus is a nonmetal, chlorine's a nonmetal. That's going to be a covalent bond. All right. The second one has a sodium and an oxygen. And if you look on the periodic table, sodium is a metal, oxygen, of course, a nonmetal. That's going to be ionic. And it's because of the metallic sodium that you've got that going on. Now, the next one has a sulfur and 3 oxygens. Sulfur and oxygen are both nonmetals, and if you have just nonmetals, that's going to be covalent. And it might be tempting to think that the next one is also covalent because sulfur and oxygen's there, but you've got a calcium, and calcium is a metal on the periodic table. So this SO3 is actually not the same as the previous SO3. The SO3 with calcium is actually the sulfite ion. It's a polyatomic ion. Remember, if there's 3 or more types of ions, you're going to have a polyatomic ion. And if you have a polyatomic ion, it is ionic, all right? Sulfite is -2, calcium's +2. That's going to be an ionic system. So polyatomic ions also mean you're going to have ionic bonds. The last one, though, antimony and arsenic. And antimony and arsenic are both metalloids. And metalloids can act like metals, and sometimes they act like nonmetals. Who knows what that one's going to do? If you've got 2 metalloids together, they could be ionic, they could be covalent, they could be some kind of split things. That would be rough. That would be hard to know. I wouldn't ask you a question like that, but it's a great learning experience. Now, why this is important is because how you name the compound is going to be different if you've got something covalent and ionic. We went through the ionics where you have fixed charge metals and variable charge metals. And the second one gets IDE, and you put a Roman numeral by the variable charge metal, and you make sure everything is neutral. Covalent is going to be quite different, like we're going to see. And the rules for covalent are only for covalent, and the rules for ionic are only for ionics. When a covalent compound happens, there is actually a special order that chemists use to talk about it. And as an example of what I mean by this, the most famous covalent compound, I would argue right now, is probably CO2, carbon dioxide. And if you've ever been awake and seen a newscast or anything, I mean, everybody calls it carbon dioxide or CO2. No one calls it dioxide carbon or O2C. There's a reason for that. The formulas of covalent compounds, you always have the less electronegative element first and the more electronegative element last. Now, another way to interpret this, because electronegative is weird, the more metallic-like element goes first, and the element which is less like a metal goes last. So on the periodic table, carbon is closer to the metals than oxygen is. So carbon always goes first and oxygen always goes last. And that's why it's CO2. And you've probably already picked up on that carbon dioxide. We changed oxygen to oxide just like we did in the ionic compounds. We're going to do that kind of thing here as well. So again, when you're naming one of these covalent compounds, more metallic-ish element first, and the less metallic-like element goes last, and we're going to give it an IDE ending too. The Greek prefixes are also used. So notice it was carbon dioxide, all right? Di is the Greek prefix for 2. And the way to indicate the number of atoms is with these Greek prefixes. And there's some rules. We'll talk about that in a little bit. This is the list of the Greek prefixes, 1 through 10. They do go on past that, but it's very rare to use it. Most of the time in my world, I use 1 through 8. Once in a while, 9 and 10. I haven't used 11 for a long, long time. But anyway, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And you've probably heard some of these before, all right? So like octa, octane, all right? A pentagram is penta, that's 5-sided geometry figures instead of penta, what we're doing. But these things have some kind of use for in the real world too. Let's say we're going to name these things BCl3. Now, these formulas are there for a reason. It's BCl3, not Cl3b, because boron is more metallic, chlorine less metallic. So to name them, you just have the name of the first thing, boron. If there's more than one, you use a Greek prefix. So Greek prefix for 3 is tri. Chlorine becomes chloride. This thing is just going to be boron trichloride. Pretty simple. The next one is NO2. And again, this is always listed this way because nitrogen is more like a metal and oxygen is less like a metal. But anyway, just like before, first element by itself, nitrogen. Greek prefix for two oxygens is di. Turn oxygen to oxide, nitrogen dioxide. Here's another example, sulfur by itself. Then there's three oxygens, so that's a trioxide, sulfur trioxide. These are usually pretty chill to figure out. They're a little easier, I think, than the ionics, but remember, these rules only apply when you have nonmetals coming together with nonmetals. Here's some examples to give us some more practice with these. These are all covalent bonded molecules. Now, the first one there is N2O5. In all the examples we've seen so far, there's only been one of the first atom, and we haven't called them mono. So, for example, CO2 is not monocarbon dioxide, it's carbon dioxide. However, if there is more than one of the first one, you do put a Greek prefix on it. So N2O5 would be dinitrogen, and that tells the chemist that you've got two N's. 5 is penta, and oxygen is oxide. So let's call this dinitrogen pentaoxide. The next one, sulfur dioxide, one sulfur, two oxygens, not too bad. The next one, oxygen difluoride. Notice that oxygen here is not oxide because it is more metallic than fluorine. Fluorine is, we'll see, the only one that can trump oxygen here. The next one, diphosphorus trioxide. Again, we're putting a di in front of phosphorus here because there's more than one. We don't put a Greek prefix on the first one if there is only one, but if there's more than one, we do. But you always put a Greek prefix on the last one. So the next one is a nitrogen. That's no problem. And it might be tempted to call it just nitrogen oxide. But the official name here, nitrogen monoxide. And you can call it monooxide. I'm not worried about that, but people usually drop a double vowel. But anyway, the second element always gets a Greek prefix, no exceptions. So nitrogen monoxide would be the name of that beast. The next ones are taking the names, putting them into formulas. So tetraphosphorus, tetra is 4, that's 4 phosphorus, which is P. Deca is the Greek prefix for 10, and oxide is oxygen, so we would have P4O10 on that one. Carbon dioxide, which is hopefully really familiar to you, that would be just CO2. Carbon monoxide, which is different. Mono is 1, drop in the double O, but you can put it in if you want to. That would be 1 carbon and 1 oxygen. And finally, the last one, nitrogen dioxide, 1 nitrogen, 2 oxygens. And like on the other ones, the more you practice, the more you can conquer these skills. None of them are hard. You just need to have spend some time with them. There's also another weird thing that happens that's usually thrown into this area of learning. Most of the atoms, when they're neutral on the periodic table, exists by themselves, all right? And so, for example, we've seen things like sodium, all right? Sodium is really happy being just individual sodium atoms. And carbon, we'll say, is usually happy being just by itself. But there are 7 elements which always appear in pairs. And these are called the 7 diatomics. So if you look, for example, a little hydrogen right there, it's listed as H2. Hydrogen, one of the diatomics, all right, always comes in a pair. It's very rare in normal conditions to see hydrogen by itself. Now, right under hydrogen is lithium. Lithium is not one of the diatomics. Lithium is happy being by itself, all right? But hydrogen always wants to have a pair. So you've got to know these. They're going to be really important in the sections coming up. One of the ways that sometimes people learn the 7 diatomics is through what's called Hankel-Briff. And Hankel-Briff, if that works for you, H is H2, O is O2, N is N2, Cl2, Br2, I2, F2, etc. Those are the 7 diatomics, and that's a cool way to learn it. My personal favorite, though, is Have No Fear of Ice Clear Brew. I don't know, for some reason that works for me. I have no idea. Anyway, each of those letters is one of the 7 diatomics. Have No Fear of Ice Clear Brew, HNFOICLBR. So you can use Uncle Briff, you can use my Have No Fear of Ice Clear Brew, whatever you want to do. Just realize that these 7 do exist in pairs, and that's something you got to take into account when you're doing things. That's it for Chapter 3, Part 1. Make sure you practice the nomenclature, and we'll do a lab and stuff and kind of figure this stuff out too. If you have questions at any time, be sure and contact me. I'm more than happy to help. Have a wonderful day.